My name is Mariusz Postel. I invite you to join a lesson on external data management. This contributes to the practical programming education track. Programming in practice systematically applies engineering principles to the design, development and testing of algorithms and programs. It is part of the software engineering field, which includes sequential, adaptive, concurrent, real-time and distributed programming. It also includes external data management. The main goal of this lesson is to understand how to create and use method references similar to method pointers. A method reference and a method pointer are ideas used in different programming languages, and they serve different functions. Hopefully, I will keep the discussion broad enough to be useful and applicable. To make it practical, all examples are prepared using C# programming language. Learning about delegates and events is crucial for mastering event-driven programming and creating flexible, maintainable, and decoupled code. Delegates and events enable different parts of a program to communicate without tightly coupling them. Delegates are like function pointers. They allow you to pass methods as parameters, facilitating callbacks. Events are built on delegates and are used to notify subscribers of a condition change. There is a strong connection between direct and functional programming.
As usual, let's start defining the main objectives of this presentation by defining the topics we may encounter in the context of the method reference applicability. I will try to keep the discussion general enough to be useful generally, but make it practical. All examples are prepared using C# programming language. According to the Copilot research, a delegate is someone authorized to represent others. To paraphrase this definition, in terms of a programming language, the delegate is a construct representing another language construct. Consequently, using object-oriented programming terminology, a delegate is an object wrapping a reference to a method, an action that happens. The method is invoked while the delegate is triggered. Simplifying, delegate represents an activity. Continuing the Copilot research, event refers to an occurrence or happening that involves one or more entities and can be described by a verb or action. To paraphrase this definition, in terms of a programming language, the event is an action, block of statements, invoked and executed using a computer machine. Consequently, using object-oriented programming terminology, an event may be recognized as an object wrapping a reference to a method, an action that happens. The method is invoked while the event is triggered. Simplifying, an event represents activity. Hence, in the context of program engineering, despite the colloquial meanings of both terms being completely different, it seems that both terms can be implemented similarly. However, before implementation, we must learn more details concerning both terms. The most important thing is the difference between them, which helps address the problem of why we need both terms. Sometimes we must deal with the ability of an entity to have more than one form. This multiformity should allow us to perform a single action differently. Commonly, this heterogeneity we call polymorphism. The polymorphism may be implemented by applying abstraction and inheritance known as a pilar concept in object-oriented programming. Hence, the first question we must address is, how to deal with the behavior heterogeneity? To implement interoperability of program parties, the first problem we must face is a control flow. The control flow may be recognized as the order in which statements of a program are executed. Control flow may be implemented using control statements, methods invocation, and delegate concepts. To deploy data transfer, interoperable parties must understand the transferred data, have access to a value holder variable, and be aware that the data is available. To avoid time-wasting polling to check if there is new data available, a notification operation must be enforced, as a result of the assignment. Events are not always coupled directly with data. For example, it is a case if we are waiting for the end of the computation and don't care about the result. Concluding, considering communication between interoperable parties, we must enforce control flow, data transfer, and event notification. A key to understanding programming and practice-related topics is a good understanding of the object-oriented programming concept. Sometimes we must deal with the ability of an entity to have more than one form. For example, a drawing may be a circle, square, or rectangle, to name only a few simple shapes. It also has behavioral consequences. This multiformity should allow us to perform a single action differently, such as area calculation. Commonly, this heterogeneity we call polymorphism. Polymorphism is a Greek word that means multiformity. This way we are recognizing polymorphism as a problem to be implemented. To implement polymorphism in the algorithm, we need appropriate tools and programming patterns. Again, object-oriented programming concept deployment is the best proposal we know today to implement the polymorphism. By design, the object-oriented programming concept allows us to create reference type instances dynamically. It may be recognized as a concept aimed at data management. Similarly, control flow management activity should be available in an object-oriented programming language. This concept may be implemented by applying the delegate concept, namely, a possibility of indirect execution of a method, by triggering an object wrapping a reference to this method. In this approach, the pointed-out method is invoked without utilizing its identifier. An abstract class, intentionally, doesn't provide all implementation details and must be implemented by derived classes before instantiation. An example of an abstract definition is an abstract method that does not have a block. Abstract methods define only the signature. The same approach could be applied to delegates to make the proposal type safe. In this context, delegate types may be recognized as an abstract representation of methods with precisely defined signatures and return types. Similarly, to instantiate a delegate type, the method block must be specified. There are many reasons why delegates could be useful for program design. My point is that the most important thing for delegates is that as a result, we can split usage of the definition and its implementation, for example to allow polymorphism. By polymorphism, I mean two or more implementations of the same action definition. In other words, the final behavior depends on the implementation provider. It could also allow postponing implementation for some reasons. Hence, the problem that must be addressed is a definition, describing what the delegate is in the context of object-oriented programming. To make the examination practical, the definition must be provided in the context of examples in part covering implementation. Information technology and computer science have provided society with a variety of distributed applications. By design, the deployment of this kind of application has to focus primarily on machine-to-machine communication. By design, for this kind of interoperability, applications are executed on geographically spread nodes interconnected by a communication network. Here I must stress that the distributed programming that is a vital part of programming and practice education path is far beyond our interest scope for now. Topics related to communication are not only typical for distributed applications. Similar ones must be considered in the context of sequential programming. In other words, the main challenge we will face is how to implement communication between program interoperable parties, despite their architecture and relationship of them. In this context, communications implies data transfer and event notification. In conclusion, the main challenge we will face is how to implement control flow, data transfer, and event notification in practice. We will talk about internal communication only, avoiding touching the topics related to networking. To implement program parties interoperability, the first problem we must face is a control flow. The control flow may be recognized as the order in which statements or method calls of a program are executed. Control flow may be controlled using control statements, method invocations, and delegate. The next option for implementation of the control flow for program interoperable parties is the callback program design pattern. In general, a callback pattern is a method passed into another method as an argument. using a kind of method pointer. Arguments are the actual values that are passed to the method when it is called. This value is passed to the method, while it is invoked and may be used to invoke the pointed method, to execute its sequence of statements. In other words, it means invocation of methods using variables, precisely speaking formal parameters. Parameters are variables listed as part of a method's definition. They act as placeholders for the values that will be passed to the method. Data transfer refers to assigning a new value to a variable. The data transfer object may be used to convey a value. DTO is a simple, lightweight object wrapping data transferred between interoperable program parties. Hence, they typically contain only data and no business logic implementation, making them straightforward for transferring new values via a variable. The data transfer may be considered an assignment of a new value to a variable by its producer. A new value, data, may be freely read and utilized if the variable is visible to the data consumer. To make program parts interoperable, even a brilliant idea is not enough. We need a data transfer activity. To deploy and practice data transfer, interoperable parties must understand it, have access to the value holder, and be aware that the data is ready to be absorbed. Theoretically, we do not need to bother with the problem of the common meaning of the data by interoperable parties, while defining data transfer in the context of strictly typed data. Strictly typed data refers to a programming concept where each variable is explicitly declared with a specific data type, and this type cannot change throughout the variable's lifetime. It should engage the usage of dedicated instead of universal types. Let me give you an example. The float type may be used to represent area, length, age, etc. This topic is far beyond our scope of examination, and it is assumed for further investigation that the strict typing concept addresses this problem entirely. Hence, the requirements may be reduced, and it could be stated that to absorb the data, consumers must only have access to value holders and be aware that new data is available. Access to a variable means that the variable responsible for being the value holder must be visible to the consumer. The consumer reads the value and processes it after it is produced and notified. It leads to a typical producer-consumer programming design pattern. To avoid time wasting polling checking, if new data is available, a notification operation must be enforced as a result of the assignment. Notification may be considered as an operation, pushing a notice that a condition has been met. For example, notification that new data is available. To notify the consumer that new data has been assigned, the property concept may be applied. A property is a member of a type that provides a flexible mechanism to read, write, or compute the value of a variable. Properties consist of special methods, called accessors, to access private variables in a controlled way. A property consists of two accessors. GetAccessor, a block, sequence of instructions, invoked to return the current value. SetAccessor, a block, sequence of instructions, invoked to assign a new value. From the producer's point of view, a property looks like a variable. After assigning a new value to the property, the setAccessor is invoked, and may notify that a new value is just assigned. The main drawback of this solution is the many-to-one multiplicity relationship between producers and consumers. This relationship limits the applicability scope. To overcome this drawback, a various approach must be applied. The most important conclusion from this interoperability implementation is that the notification is implemented by the invocation of a block, a sequence of instructions. The one-to-many multiplicity relationship between producers and consumers may be implemented by applying the delegate concept. Delegate value is an object wrapping a method reference. The method may be invoked using this value. Delegate values are type safe. It means that the referenced method signature, parameters and return type must be compatible with the predefined signature of a delegate type. Using delegate variables, the one-to-many multiplicity relationship scenario may be implemented by grouping delegates interested in absorbing and getting noticed about the availability of new data. In this scenario, data transfer is realized using the parameters of referenced methods. Improved, the one-to-many multiplicity relationship between producers and consumers may be implemented by applying the publisher-subscriber program design pattern. The publisher-subscriber scenario is used where interoperable parties ought to interact without being tightly coupled. Value producers, called publishers, in this concept, do not assign new values directly to specific variables visible by consumers. Called subscribers in this model, but instead categorize the values into topics without knowledge about which subscribers, if any, there may be. Similarly, subscribers express interest in one or more topics and only receive values that are of interest. In this scenario, the publishers and subscribers are loosely coupled. An improvement related to the producer-consumer interoperability design pattern results from an unsymmetrical relationship between publishers and subscribers. It means that a subscriber, in contrast to consumers, must not have any impact on other subscribers. The publisher is responsible for sending data to all subscribers alone, and is also the interchange channel owner. To follow strict typing principles, the publisher-subscriber concept must be implemented in the context of the type concept, considering object-oriented programming. This concept must ensure data transfer and notification, allowing subscribers to avoid active polling availability of new data while waiting. In the implementation of a many-to-many interoperability relationship, the identification of data sources is also vital. It causes additional requirements related to subscribers. This scenario may be implemented using the event concept. According to this concept, data transfer is realized using the parameters of handlers. A handler typically refers to an event handler. An event handler is a method executed in response to a specific event. Let me recall that an event is something that happens or takes place asynchronously. Whereas in the context of program engineering, an event may be implemented as the Boolean condition change. Hence, event notification may be considered an operation pushing a notice that an awaited condition has been met. Previously, we used notifications while new data was available. Events are not always coupled directly with data. For example, it is a case if we are waiting for the end of the computation and don't care about the result. The next example is a mouse click recognized as an action performed by pressing and releasing a button on a computer mouse. By notification of these events, we are pointing out that the result and screen pointer position are ready to be absorbed. A screen pointer, also known as a mouse pointer or cursor, is a graphical image on a computer screen that moves in response to the movements of a pointing device, such as a mouse, touchpad, or stylus. It indicates where actions like clicks, selections, and other interactions occur on the screen. Event notification involves notification that a specific condition has been met. It may be implemented by invoking handlers. A handler refers to an event handler. An event handler is a method executed in response to a specific event. In other words, an event handler is a method that gets executed in response to a particular event. This method contains the code to be executed when the event is triggered. To avoid further theoretical discussion, let's analyze the available options the selected programming language provides. I have prepared a few examples to explain how control flow, data transfer, and event notification may be implemented. Let me stress that they may be implemented using a variety of program design patterns, but special attention to object-oriented programming is applied. Hopefully, this way we can implement polymorphic methods invocation. Because while invoking methods, all current parameters must be provided, data transfer is also possible this way. To follow me, clone the TP repository, and switch to 5, 3, 1, alpha tag. Finally, the external data management solution can be opened in MS Visual Studio. The code samples related to the delegate can be found in the delegate example class. The code samples are expanded by using located in the delegate example unit test class. According to the Natural Language Dictionary, a delegate is someone authorized to represent others. To paraphrase this definition, in terms of a programming language, the delegate is a construct representing another language construct. Consequently, using object-oriented programming terminology, a delegate is an object wrapping a reference to a method. The method may be invoked using this delegate. Referring to the introduction to the delegate concept, we can state that it is an ambiguous term. However, in the common sense of software developers, it means a concept that allows invoking a group of methods in a type-safe manner. Type safety means that the pointed out method's signature and return value type comply with the predefined type. In the programming language, this ambiguity is addressed by the definition of the following terms: keyword, type, variable, and value. Let's examine this implementation using code samples. Hence, the delegate is also a keyword used to declare a delegate type. The delegate type represents objects wrapping reference to a method compliant with a defined signature and return type. A delegate variable is a holder of an object, if any, containing a group of delegate values compliant with a delegate type that can be subject to well-defined operations, including but not limited to the pointed methods invocation. In the delegate example unit test class, there are snippets that we can use to examine common features related to the usage of the delegate. The delegate type is the reference type. By design, the delegate value is instantiated using a new operator, as in this code snippet. A new instantiated delegate value is assigned to a variable. Applying more concise syntax, the new operator and type identifier are removed. In this case, using only the method name or definition of the anonymous function, it is possible to instantiate the delegate value as in this code snippet. The anonymous function has been implemented using lambda expression syntax in this code snippet. It is an equivalent method to the named original one. Following the object-oriented programming principles, a delegate value is an instance of the delegate type, wrapping a reference to a method compliant with the signature and return type defined by a delegate type. It means that pointed out methods don't have to match the delegate type exactly. They must be compatible only. Assigning null to a delegate variable effectively means it doesn't reference any method. Consequently, the invocation of methods causes an exception. To prevent throwing an exception, null conditional operator may be applied. As a result, nothing happens if the delegate variable evaluates to null. Delegate can be invoked just like a method. Indirect invocation using a delegate variable and direct invocation using the method identifier yield the same result. The overflow test method demonstrates that methods invoked using delegates behave as regular methods, where overflow may occur. For example, a delegate variable may contain references to many methods. Multicast test method is a code sample of this scenario. You can add methods to delegate variables, and remove them. In other words, delegate values can be grouped using a delegate variable. As a result, multiple methods can be called on a single notification of the delegate variable. Hence, the one-to-many multiplicity relationship scenario may be implemented this way. From this example, we can learn how to implement a group of delegates interested in absorbing and getting noted about the availability of new data, by adding them to a delegate variable. After noting this variable, all the associated methods are called, in the order they were added. In this case, the delegate variable may be considered, as a list of delegate values, simplifying a method's chain. The result of the grouped invocation is equal to a value returned by the last method from the chain. If, for some reason, the order of adding the delegate values is unknown, for example, the variable is public and can be used by many participants, while noting the delegate variable, it must be assumed that the methods are invoked in random order. In this case, the delegate variable must be considered a set of delegate values, and using the return value in further processing can be questioned. Delegates can be passed as arguments to methods. In other words, this scenario allows passing methods as parameters to other methods. Hence, this programming design pattern is named callback. Delegates are a popular form used to implement callbacks. Using the delegate-based approach, we will examine this mechanism to implement data transfer in addition to control flow. The sample code is the anonymous functions class. It contains an implementation of a state machine. The implementation of a state machine can be approached in several ways. This sample code uses an object-oriented programming approach to illustrate the concept. The state enum defines the states of the machine. A transition is the process of moving from one state to another in response to an action. Actions that can be applied against this state machine are grouped in the iStateHandler interface. Not all actions are allowed for all states. The current state is available through the current state property. In the context of delegate usage, the most important is the consistency check method. This method is used only for debugging purposes. Thanks to the conditional attribute, it is removed from the final version of the code. To be silently removable by the compiler, it must have neither return value nor out parameters. Hence, to implement a diagnostic data transfer mechanism, the delegate type parameter is used. The test result parameter is of the delegate type. As a result, it is a variable and may contain a reference to a method invoked to transfer the diagnostic data. Because, while raising this delegate variable, the null value of this parameter is not handled, this variable must not be null to prevent throwing an exception. This delegate parameter is raised inside this diagnostic method to transfer the diagnostic result. It is the main reason why we name this scenario callback. Delegate is an ambiguous term. Hence, if from the context it is not clear when referring to delegate, we should always directly state, if we are talking about a concept, type, variable, or value. The main drawback of the delegate implementation is the possibility of modifying unconditionally by users the content of the delegate variable, exposed as a public member of a type. As a result, this solution is prone to disruption of the call chain by the data consumers. Because in the callback scenario, the current argument of a method parameter value is instantiated locally, it is more robust against the side effect. The code samples, related to events, can be found in the anonymous functions class. The code snippets are expanded using unit tests, added to the anonymous functions unit test class. In this class, the most vital testing method is event test method. Getting straight to the point, we commence the sample code examination from the declaration of the onState changed event. It can be found in this line. We see the event keyword here, followed by an identifier. After examining the identifier declaration, we can learn that it is the name of the delegate type. We have the next identifier here. It is the name of this event. Except event keyword, the entire declaration in this line of code resembles a declaration of a delegate variable. Hence, in this declaration, the keyword event plays the role of delegate variable modifier. The only question is how the event modifier changes the usage of this delegate variable. In this code snippet, the event is a member of the anonymous functions class. It enables notifications to be triggered after changing the state. Users interested in being notified about state changes can attach executable code for events by supplying event handlers. Event handlers are delegate instances added to the event and executed in response to notification. After notification of the event, all added event handlers are invoked. Event users can add or remove their event handlers to or from an event. To explain the difference between events and delegates, we must again refer to the type concept. All types including delegates define a set of allowed values and a set of operations that may be applied to values belonging to the type. For all types except the events, access modifiers used to declare the visibility of a variable applies to all operations defined by this type as well. Using the keyword event introduces a selective availability policy that restricts the scope of some operations' visibility, including but not limited to notification. For example, the notification operation can only be raised inside the class where the event is declared. In this line of sample code, we can examine local notification. In other words, the notification is inside the class declaring the event. Similarly, we may try to raise notifications outside this class boundary, for example, in the unit test class. After uncommenting this code instruction in the unit test, the compiler complains informing that this operation execution is limited to inside the source class only. It ensures that notification can be raised only inside the owner class of an event. The same result is, if we try to remove all event handles, by assigning null to the event. It prevents any impact on the call chain outside the owner of the event. Removing the event keyword from the source definition causes the errors to disappear. The goal of this intentional asymmetry is to improve robustness. For event, it defines two kinds of event users. First, owners, containing the declaration of events, also called publishers, must be distinguished. Whereas, users of events, also called subscribers, are external users of events, with limited possibility to execute all operations despite the event access modifier. In other words, the main reason is to improve robustness by distinguishing and separating publisher and subscriber roles of event users. In other words, it means a selective availability of operations impacting all delegate instances added to the event. Subscribers express their willingness to absorb data and be notified about the availability of new data by adding event handlers to visible events. They are the destination of the communication by adding a reference to event handlers that are to be invoked as a result of raising the event by the publisher. This relationship multiplicity between publishers and subscribers is one-to-many. As the name says, the publisher is recognized as a class that is a source of communication realized using events. Therefore, only inside this class events can be notified, and, as a result, associated methods, pointed out by the event, are invoked. Hence we can recognize the notification raising operation as always private despite the accessor modifier of the delegate variable. It is also possible to implement the many-to-many relationship. To facilitate implementation of this relationship, the definition of event handlers contains a dedicated parameter to be used for transferring reference to the data source. The publisher-subscriber model of party interoperability is supported by the event concept. From the examined examples, we can derive that the main reason for publisher-subscriber communication in sequential programming implementation is the possibility of improving the deployment robustness. The main goal is obtained as a result of limiting the scope of operations targeting all subscribers to the event owner inside. This approach assumes that the multiplicity relationship between publishers and subscribers is one-to-many. Thank you for watching. To follow me, watch or star the repository with the extended examples on GitHub. If you have questions or doubts, contact me by Gmail. com@programmingandpractice24. Let me invite you to visit Mariusz Postal's profile on C# Corner.